All right, everyone, we are going to basically finish off our last lesson of the year, like official lesson, I guess, because 7.5 is the last bit. So yay for us. But before that, I do need to make sure that you're very comfortable with future value of an annuity, because I am going to introduce a new formula today. Um, also note, after today, you will have all the pieces you need for both your optional assignment as well as your quest. And present value, as I was just saying prior to the recording, not only do you need it for both your quest and the optional assignment, it is in what I consider to be one of the most applicable, most useful formulas you may use for the rest of your life, especially if we fall under the low and middle class. What do I mean by that? Present value of an annuity formula fits the context or fits the description of anything where you start big and you're trying to turn it into a zero. Things like if you have a mortgage, you have a big lump sum as debt, and you're trying to pay it off and shave off of it until it gets a zero. Things like scholarships, you have a big lump sum and you are um, basically using it to give scholarships to people until it turns to zero. I'm going to give you an example of that. Okay. So without getting too much into detail, you have to be comfortable with future value. If you are not comfortable with future value by now, I'm going to try to divide 7.4 and 7.5 perfectly evenly, but you might get a little bit confused if you haven't practiced yet. So let's recap. Telling the story. Oh, something on chat. Let me your sound doesn't creep. Oh, okay. James, I will fix your attendance in just a second. Everyone else, would you please take a look at um, the whiteboard and consider the question. You decide to make a deposit of $1,000 every month, which should ring a bell. It is a repeating term, a repeating payment. So it's going to involve R. It's not a principal. It is a geometric series. It is a annuity. The investment returns 7.2% per annum, compounded monthly. What is the future value? And I specifically use the word future value in this question because today we're talking about present value. Okay, what is the future value or final amount of this annuity after 47 years? Because again, I'm assuming you're either 17 or 18 and you're going to retire at 65. So, what is my future value? My recurring is 1,000. My rate is 0.072. My compounding period is 12, and my time is going to be 47. So my formula is going to be R, 1 plus, and right now, as opposed to copying this down, I like everyone to take out a calculator and just work through it with me. Because if you've been practicing, you will notice that this question is nothing more than um, any other question that you might have been asked, any other homework question you might have done. I realize R is supposed to be 1,000. So let me write that in. 1,000. Okay, so let's do it. Again, if you are limited in practice right now, what you're going to be doing is calculating this first in your calculator, and then whatever you have as your answer is going to be to the power of 12 times 47, which is a very large number, 500 something. And then you will subtract that entire answer with a negative one, and then you are going to divide by this fraction and then multiply by 1,000. That you could do in any order. Tell me what you get. Or rather, I'm sort of going to be going on the fly myself because I just made this question up. Please tell me if I am making a mistake by doing this with me. It's a lot. I'm going to have to do this again. I'm not sure if I'm doing it wrong or not. It seems to be a very large number, a little too large even for me. But then again, you are doing it for 47 years, so 12 times 47 minus 1 times 1,000 divided by 0.072 divided by 2. Yep, that's it. Okay, so we're all good, which I guess makes sense. I'm going to take a look at this. I'm doing this 12 times 47 years, and that's 1,000 for every single time. So your actual deposit of your own money is this. You put in $564,000, but it grows into that. Okay, which makes sense. All right. So here's another thing I'm going to ask you to do before I make a comment. Part B asks, how long does it take? So this time I'm asking for the exponent. How long does it take if I want to double this value? So taking this amount, 4,698,636.15, I'm going to multiply that by 2. If my final value happens to be double this, so this is 9,397,272 and 30 cents. Then how many years? Ah, come on. Yeah. How many years would I have to invest? Okay. And a very simple guess would be, oh, if it took that much time, 47 years to become 4 million and $4.7 million, then maybe it will take twice as much, 94 years, for that to become uh, double, right? So let's test it. Let's pretend this is 94. It's a very simple and shallow guess, but that might be the first thing you might think about. Put that into the calculator. If you actually did this for 94 years, what would that turn into? 0.072 divided by 12 plus 1 all to the power of 12 times 94 minus 1 multiplied by 1,000 divided by the fraction in the denominator. Take a look, everyone. Assuming that you've been doing it with me, I'm not going to question your calculator abilities. I'm assuming you know how to do it. But take a look at what happens if I double the time. What happens? Do I get double the value? No. Remember, the original value was 4.7 million. It was approximately 4,700,000. This is not double. This is in fact, let's see, 10 times, 20 times, 30, more than 30 times the amount. You double the time, you multiplied your value by 30 times. So clearly, times 2 versus times 30, it is not equal. It is not linear. But that shouldn't surprise you. Because take a look at my illustration. And this is the point I want to make. If this multiplication of 2 for the exponent, gave you a multiplication of 2 for the total amount of money, you would know that this relationship is supposed to be a linear one. But that's not true. Because it's an exponent, it is in fact exponential. Take a look at this diagram, right? Every amount starts slow, but as time passes, it will start to pick up. If I were to do this as a graph, This is a very tiny graph, but you're going to have to bear with me here, right? Starting with basically $1,000 in the very first amount of time. If I wanted to double that into 2,000, okay, it just adds growth. It might take a little bit of time, but 2,000 turning into 4,000, we're going to get there very, very soon. Let's pretend this was like 10 years. To go from here to here, it looks about half of that. It takes only another 5 years. And that's the power of exponential functions, right? The long story short, the longer you do this, the faster you will reach, or the longer you do this, more of this steep curve you're going to take advantage of. And this is why there are people that don't have to work a single hour in their life, but because their grandparents or their great grandparents, or basically old money has set up and they're already entered this high exponential functions area in the graph, they can continue to give a little bit of money to their siblings or to their grandchildren or great grandchildren, whatever, and it won't even make a dent. This exponent will continue to go up and up and up and up and up. And so if you go on the internet for, just for jokes or whatever, and you talk about finance, you might see this sort of like a joke slash slang, slash even like some people might even use this as an insult, right? Being a trust fund baby. Basically, many generations ago, they had a very wealthy ancestor, I guess, and they set up a trust fund for their great grandchild. And so that money was already increasing at an exponential rate. By the time this baby turned 17 years old, because the money has been in there not for 10 years, not for 20 years, not for 30 years, but for like 3 generations. That's like, what, 120 years? Can you imagine this exponent being 120 times 12, right? The amount of money in their account is already well into the 100 millions, and so they can spend whatever money they want. It won't make a dent on that exponent, on that graph. Right? So in the previous class, someone made a very interesting, I guess, interesting observation. They said, then why doesn't everyone set up a compound interest account for their child, and then when the child grows up to be a full adult, then they can capitalize on it? Have you thought of that? Okay, think about your own future. You are 17 years old. This is 2021. You are 17 years old. Okay? You start putting in $100 a year. It doesn't matter. By the time you have a child, I don't know, let's pretend you have a child when you're into your 30s. That seems to be a typical thing. So 15 extra years. So 2036, you have your child. And then after that child is born, maybe another 30 years. So if I were to try to scale it, 2066, your child might have a child. But if you take a look at how many years that is 2 generations. 15 plus another 30, that's already 45 years. And by the time your grandchild is 17 years old, that's an extra 17 years. So 45 plus 17, that is 62 years of growth. Can you imagine what this grows into even if you only started with $100 today? So I lament a little bit because my parents, when they first came to Canada, that was very close to one of the recessions in Canada. And so whatever amount of money that they put into the stock market, they basically lost it. And they weren't wise enough to know that if you leave it there, it's going to rebound. And so they lost a lot of money in the stock market. And so they've always been fearful. And so they never really taught me anything about it. And I'm not saying you should go into the stock market. I'm not saying that. Whatever investment you make, if you continue on with it, this, even if the safest way, like getting 1% a year, getting the safest investment possible, you will let it snowball as long as you keep it in there for long enough. So if your grandparents haven't started, that's okay. If your parents haven't started, that's okay. You can start it now, and 2 generations from now, your grandchildren will be like, wow, my grandpa was really smart, right? He made moves, or she made moves, or whatever. Think about it, okay? Any questions about that? Any comments? No? None? This doesn't surprise you? This is like I've known this stuff for a while. I don't know. To me, it was pretty remarkable. I'm hoping you're going to be able to take something home from that today. No thoughts? Last chance before I move on to today's lesson on PV, present value annuity. Going once, going twice. All right. Today, would you consider FV versus PV as a formula? I'm going to show you the formula first, and I want you to draw some similarities and differences from the left formula and the right formula. And from there, I think is a good place to go to our handout. Future value is basically we put in money, we put in money, we put in money, and we see it grow. Present value is actually a little bit different, and it's even more different than when I was doing present value for regular geometric series compound interest. Okay, it's a bit more complex than that. But let me first try to explain. But it makes more sense, I think, if we start with the formula. So future value is a recurring amount R multiplied by our ratio 1 plus R divided by N to the power of NT minus 1 divided by R over N. Present value is basically the same thing, but the minus 1 is actually now positive 1 minus the ratio, and the exponent is a negative. Can you sort of see a mirror image parallel between future value and present value? It's really important. A lot of students forget the fact that instead of subtracting by 1, you are subtracting from 1. So when you're plugging into the equation, please be careful that you are not doing the bracket portion here and then subtracting with 1. You're actually doing the bracket portion here and then doing 1 minus whatever your answer is. The next thing I'd like you to consider is how the exponent here is a positive. For the present value, the exponent is actually a negative. Whatever your compound period is, whatever the amount of year is, after you calculate the multiplication, stick a negative in front of it. That's your exponent. Gotta be careful. All right? So let's see how we can use this question, how you can use this formula, how this present value annuity is supposed to be used in a very different scenario, a different story versus the future value. Okay? Let's start with the handout, and then I'm going to start drawing more and more details so that you don't confuse it with future value. This sheet might look familiar. In chapter 7.4, I gave you another sheet that had this kind of timeline. So I'm going to give you another example in hopes that the timeline will help you visualize it better. Present value of an annuity. Take a look at my grammar. I'm amazing. Present value of an annuity. Shaving down a present value to become a value of 0 in the future. I'll say it one more time. The present value of an annuity, this formula right here, PV equals R 1 minus this with a negative exponent. Okay. This formula is used when you have something right now and you want to turn it into a 0. You're making the value smaller and smaller and turning it into a 0. When the heck would you ever have a scenario where you have a certain lump sum now and you're trying to turn it into a 0? Think about it. Once, going twice.
A
You might.
mortgage?
Yes. Okay. If it's a mortgage, you basically took out a huge lump sum and you're trying to turn that into a zero because you don't want to be in debt. Another one could be like a scholarship, right? What does that mean? It means someone put in a big lump sum of money inside the bank, and then every year you take like $1,000 and give it to a student. The next, you put $1,000 and you give it to a student. Next year, you put $1,000 and you put it into a student. And you keep on doing that until it becomes a zero. So
I'm
things like
paying
more,
the loan and stuff too.
absolutely. OSAP, so your university loans, okay? You borrow a buttload of money just to get through school, which this is recording, but I don't care. If you are going to school because you have nothing better to do, if you're going to university because you have nothing better to do, I don't think it's a good use of your money. Okay, don't go to university just because people are telling you to. Go there with a dream. I'm not joking around. Okay, this is from a teacher here. Anyways, anything. So you have some kind of pot of money and you're trying to turn that into a zero. Usually that's in a negative connotation because you talk about that as debt. You have this big lump of debt and you're trying to turn debt into zero. It doesn't have to be that way. So I'm going to give you a scenario right here. So if you didn't know already, this is actually a true example. Northern Northern Secondary gives a math scholarship of $1,000 to a graduating student, a grade 12 student, every year if you apply for it. Why is it blue? That was weird. Why is my life like this? Does anyone know why it's like so foggy now? Anyone?
I think it looks fine from at least my end, our end.
Hey, give me a second. I feel like my Chrome might have like froze or something. All right, give me a sec. Courses, open it up. Chapter 7.5. All right, it's white once again. Nice. Share screen. There it is. Okay. Okay. So this is a true thing. Northern issues a math scholarship of $1,000. It was first established in 1945 by a former Northern graduate. I believe he became an engineer or something like that, became successful, and wanted to do something for future graduates in that school. The scholarship fund, this is was something I made up. It earns an interest of 3.6% compounded annually. If there was enough money to invest to pay out a scholarship for 100 years into the future from 1945, how much money did that graduate put in at the time of inception? Okay, so let's try it. I need a little bit of space. This is 1945, and I want one student to have $1,000. In the next year, this scholarship will pay out another $1,000 to a student, a worthy student who would like to pursue maths. Okay, so on and so forth. And then 100 years from now would be 2044, because it includes 1945 as one of the years. 2044, this is 2043, and 2042. So $1,000 every single year. At the same time, let's remember the rate is 0.036. My n value is a 1, and my time is 100 years. Everyone with me?
Yep.
Okay, So here's the part that makes this different from future value. Okay? Let's pretend it's 1945. 1945, I need $1,000 right now. But 1946 is a year away. If I have, if I need $1,000 for next year, how much do I need now for it to grow 1 year to become 1,000? What I'm trying to say is my final value is 1,000. What is the principal that I multiply with my growth rate to become 1,000? What I'm asking for is a compound interest. If my final amount is 1,000, what is the principal that multiplies with my 1 plus r over n times t? So in this case, it's 1 plus rate is 0.036 divided by 1 because it's annually, so I'm not going to write that. And how many years does it have to gain interest? Just one. So how do I calculate P? P is basically divide by that amount, 1.036. And of course, if you're dividing by something, you can technically say it's multiply. You can multiply it by its reciprocal by writing 1,000 multiplied by 1.036 to the power of a negative 1, right? Because that is equal to this. So, but I'm writing it as an exponent of negative 1 for a reason, which you might have guessed because of the formula that we're going to use. Okay, so let me rewrite this. I'm going to bring this as is over here. Oh, I don't have enough space. Let me rewrite it then. This is going to be 1,000 times 1.036 to the power of negative 1 because it had 1 year to gain interest. And could someone do that in the calculator for me while I set this other one up? Someone?
Uh, I got 965.25.
965.25. Sounds about right. Okay? So if I want to give a student $1,000 next year, I only need $965 right now, right? And Josh, in the same way, if I want to give a student $1,000 2 years from now, how much do I need now? Can you solve that next one for me?
931.71.
931.71. That sounds about right. So over 1 year and over 2 years, I earned about 70 bucks. Right? Over 1 year, I earned just about $35. This is about 35, about 35. Okay? That makes sense. So all the way to the end, this one had, let's see, 95, so 1 year, 2 years, so 99, 98, 97 years to grow. So this would be 1,000, 1.036 to the power of negative 97. Next one, all the way to the end. And of course, same one, all the way to the end. Okay. I think you get the point. I just want to show you what that last one is going to be. How much money do I need if I'm going to give someone $1,000 99 years from now? Oh, sorry. Yeah, 99 years from now. What does that turn into? According to my calculation, you need $30.16, and it will grow into $1,000 after 99 years. So just like before, if I want to know how much I need now, I need to add 1,000, 965, 931, add this amount, add every single amount in the middle, all the way up to $30.16 as my last number. Who's got time for that? Nobody. This, though, can also be a form of geometric series. And so let's use our present value formula. How much do I need now for it to turn into $1,000 pieces, slowly shaving away from my current value? So my recurring amount is 1,000. This is 1 minus. And if you haven't done so already, now is the time to take out a calculator. You're practicing a new formula, so no one should be waiting for me to do work for them. Okay? Try it out yourself. Divided by 1, negative exponent of 1 times 100, so 100, divided by 0.036. How much do I need now if I wanted to pay out for 100 years? Hmm, how is that? I'll give you a minute. Please just try it. And if you don't quite get it, we'll work through it together. But if you do, I'm going to assume that the silence means you got it.
Wait, do you have to write the negative exponent in your calculator, or do you have to multiply by the reciprocal, like when you're putting it into your
Oh,
calc?
just you can plug in a negative 100. Just in case, depending on what your calculator is, make sure this is in a bracket. If it's scientific, sometimes by syntax error, it might make a mistake. So keeping the negative with the 100 might be a good idea. Okay. It's generally silent, so I'm going to assume that people are able to reach this. Is everyone okay?
Yeah.
Yeah? Anyone else? Okay, so here is a very a decent what is it example of what present value is, but not all examples are going to be like this. So again, formula is one thing and reading the question is another. I want to show you another illustration to try to map out exactly what it is that we're doing with present value compared to future value. Okay, so as I was drawing before, future value is you pushing a snowball, right? And then, sorry, you know what? Let me just draw this. Okay, you're pushing a snowball, You're pushing a snowball, and then you are pushing a snowball. Okay? So what's happening is this. So for future value, right? What you're doing is actually you are putting some money in and you're watching the snowball roll to be a bigger size. And when it gets to a certain size, you are putting more into the snowball while it rolls to get bigger. And while it's bigger, you get more into the snowball and you're letting it roll. And every single step of the way, you're putting in more as it gets bigger. So essentially, you could think about it as it gets bigger in two different sources. One is your continuous deposit and a continuous increase in interest. More deposit and more interest. More deposit and more interest. And sooner or later, it picks up so much that it essentially rolls on its own and you don't have to add anything to it, it just gets too big. For a present value, it's actually the opposite. You have presently, right now, a big sum. I don't know what that is, right? But what you're doing in the present value scenario is trying to make that snowball as small as possible until it becomes nothing. What do I mean? Well, you start with a big lump sum, and then you could be, let's say, you're pay back debt, right? So if this snowball is debt, you are taking away from the debt by paying into it, right? You pay them back. So the snowball gets smaller. However, the snowball continues rolling. So you are trying to make the snowball small, but the snowball rolls and gets bigger. You pay back again. And so the snowball gets smaller, but it rolls bigger. It basically, what you are doing and what the snowball is doing are opposites. You're fighting against the snowball. You see it? It doesn't have to be debt. What if it's a scholarship, just like our example? We have a pot of money, so in this case, $26,000, right, for the Northern Scholarship, and you give a student $1,000, making this pot smaller. But the pot continues to grow or snowball, it rolls and earns interest because it still is in part of an investment. And then you pay another student, it rolls to get bigger. You pay out, the snowball gets smaller, but it rolls to get bigger. You pay out 1,000, the ball gets smaller, but it rolls to get bigger. Right? Present value, you are to use this equation or this formula when you notice that you start with a certain amount and you're trying to make it into a zero. Whether it's good or bad, you're trying to make this into zero. Whereas future value, you're trying to make it as big as possible. So when you read the story, and I'm going to present to you a couple of scenarios, when you read the story, please check to see which formula it is. Because I have seen so many people not able to essentially read correctly and use the wrong formula, essentially not getting any marks for it because they weren't able to think critically enough and notice the difference. So in short, your goal for chapter 7.5 is to be able to read carefully. Let's get some practice with that. Go back to your sheet. I believe I gave you only three example questions in the sheet for 7.5, but there's a whole bunch of textbook questions you can work from as well. Okay? Here it is. Question 1. Clara's Uncle Ron left her $500,000. That's very generous. But at the same time, maybe it's because Uncle Ron passed away. That's sad. After buying a new car and taking a trip, she has $450,000 left. So we're not using 50,000 here, 500,000 here. The amount that we have right now, hint hint, is 450,000 right now. Presently, it is the present value. She decides to use this money, remaining money, to purchase an annuity to provide her with an income for the next 30 years. She buys an annuity at 6% per annum compounded annually. The annuity will provide equal amount annual payments. Determine the amount of each payment. Okay, let's write this down. The present value right now is $450,000. The rate is going to be 6%. It's going to be annual, and I want this to pay me 30 years. What is my recurring payout that I get every year? So that's all you need. Let's plug it into the equation. Just as a reminder, the equation is even I made a mistake. 1 minus 1 plus r over n negative nt divided by r over n. Okay, let's plug in numbers. 450,000. R I do not know. 1 minus 1 plus 0.06 divided by 1 nt negative 30. R divided by n 0.06 over 1. So I'm going to calculate this. I'm going to write what's supposed to be here just to make sure everyone is on the right path for the calculator. It's so easy to make silly mistakes with a negative exponent as well as 1 minus. So test your skills. You should get this. If you did find some trouble or you did not get 13.7, please stop me. But I am going to just continue ahead. Divide 450,000 with that number, giving me 269,201. Okay, that's pretty sweet. Right? If this calculation is correct, then what's happening is every year for 30 years, the bank is going to award me this much just because I have $450,000. And think about it. This is every year for 30 years. If I multiply this by 30, what does that actually equal to? It equals $980,000 and 760. Clara inherited $450,000, but what she got out of it really was almost $1 million. Why? Because she used an annuity. She had 450K and she used 33K, so 32.5, 32 point, let's just call it 33K, okay? So the snowball turned into a smaller snowball, 417K. But it was able to roll further and earn an extra plus 6%. And 6% of 417,000 is now 442K. Think about it. You use 33,000, but because there's still so much money in this snowball, when it rolls and gains interest, it's as if you only spent 8K from the pot. And that's the power of having a lump sum and letting it grow while you slowly shave away. And this continues until we get to zero. That is present value annuities.
I have a quick question.
Yes, sir.
Um, for this question, when it says determine the amount of each payment, is the
Mhm.
final answer the 32,692 or is it the 9?
Yes. You will get, Clara will get this much every year, the
Thank you.
repeating payment for 30 years. And that means for 30 years we get this much, and that's when the 450,000 will finally run out. Okay, and that's why I multiply by 30 to show you that 450,000 basically ran the 8 miles, right? Ran the long marathon and actually stretched out into almost $1 million for you because it continued to grow. Now, I'm hoping that more than the formula, the concept is clear to you, and that if it is clear to you, you should be able to apply this very easily to the mortgage situation as well as your retirement situation. Okay? So I'm going to shift gears and change up the story. You can try number two and number three on your own. I'm going to change up the story and um, play a scenario out for your retirement, just like your assignment. Now, next time I see you tomorrow afternoon, I'm going to formally go through the assignment with you so that you know exactly what you ought to be doing. If you've already started, great. You don't have to wait on me, but I wanted to do that for you. Okay? So let me clear this. I'm going to go to the whiteboard again and let us talk a little bit about this idea of retirement. Okay, I'm going to give you some numbers. Let's pretend that I want to spend, $10,000 per month on as a retiree, right? That includes, I'm going out a lot. I want to go on a small trip every month. I want to lavishly spend on my grandchildren. I want to keep up my hobbies. I want to do a whole bunch of stuff. So I need $10,000 a month, which means multiply this by 12. I need $120,000 per year. And let's pretend I'm going to live from 65 to 90 years old. I think, let's pretend 90 years old is old enough. And I'm going to pass away peacefully. I've lived the full life and I'm ready to move on. I've left enough for my children, whatever. So 25 years, $120,000 spent every year for 25 years. I need 3 million. I need 3 million, right? That's how much you're supposed to have saved up. Except it's not. Think PV. Do I need all the money I'm going to spend over 25 years immediately? No. You don't need that much in reserve and just sitting there doing nothing. What I could have is a smaller bag of cash, okay? Smaller amount of cash that will continue to grow while I spend 120,000 every year. So what is the actual amount I need if I want this kind of retirement life? So let's talk about this. The recurring payment I want my investment to give me for my retirement is this much per year. Or rather, let's make it more believable. $10,000 per month. Yep, oh, you go for it. Just if you need this extra bit, just take a look at the video. It'll be up in a bit. Hope everything is okay. Let's see. The time is still going to be, I'm going to be retired for 25 years before I pass away. I'm going to take out $10,000 every month, so my compounding period is 12. And my interest rate, you don't want anything bad happening to your retirement fund, so let's pretend we are in a safer, we're not aggressive at 8%, I don't know, even 6%? We can do 6%, right? 6% is pretty modest, I think. What is the present value that I need at the age of 65? How much do I need? Let's plug that into the formula. PV is equal to a payment of $10,000 every month, 1 minus 1 plus 0.06 divided by 12, and 25 years negative times 12, all over 0.06 divided by 12. 0.06 divided by 12 plus 1 to the power of negative 25 times 12. Is that 1 minus the answer multiplied by 10,000 divided by 0.06 divided by 12. Okay. So continue with your calculations, but I'll continue talking. Essentially, if you want to live that kind of lifestyle, you don't even have to, you just have to have half of that. And that will continue to grow. Remember, it's 6%. It's a very modest percentage for a long-term investment, right? So that could even be 7%, which means you need even less saved up by the age of 65. That's good news for us, like or people like me who's I'm basically a salaryman for the rest of my life until I retire. I don't need to make incredible amounts of money right now to retire comfortably. I just need to be able to use my future value annuity and maybe raise a million over. And that's the beauty of it. That's why in my previous question I wrote that most people think that as long as you have what $750,000, you can retire modestly, or if you have over a million, even better, you can retire comfortably. You don't need to be a multi-million dollar industry, okay, just to have, a comfort in your retirement. And that is, I think, a game changer, having a present value formula added to the future value. And so, as a heads up, that retirement assignment that I have is trying to get you to walk through a imaginary scenario where you're using the future value and the present value formula hand in hand, right? So this is um, so the first box with the future value is when you're still able to work. You can let math and compound interest help you in your favor. And then when you cross the border, which is retirement, and you're not able to work, you let compound interest work in your favor so that you can maximize the amount of money you've made. And I hope that gets you excited. Like a lavish lifestyle. So $3 million, you actually don't need to save that much at all compared to what you thought. And if you keep going, you realize that not only PV, but FV will help you. So you might even have to save even less than you thought. Next time I see you, that's tomorrow afternoon, I'm going to go in detail through your optional assignment for you. Um, and again, if you started, that's fine. But one thing I like to say is try to be as realistic, as honest, and as detailed in your numbers as possible, because the more time you put in to make this realistic, the more you'll get out of it. If you just make up numbers, you really won't get much out of it. You'll just get some marks and you basically waste time because you're not taking anything home from this. Try it. For your homework, I guess, if you haven't done the quest, you better go and do it. Okay. Number two, you still have the optional assignment that you can try. More so than that, now that you have 7.5 done, you can try the practice questions on the worksheet, on the handout, plus the textbook. And then I guess that's about it. I can't think of anything else right now. Optional assignment, practice questions. Yeah, I'll leave it at that. So these are the things that you ought to be doing. Think of what you can and cannot do by tomorrow. Even if you don't get to the optional assignment, that's okay. I would think 7.5 is important because you have to get the quest done. Any questions? No? Once? Going twice? Hmm. I notice, let's see. Is there someone that stepped out? There's less participants than when we started. Oh well. Cindy says she wasn't able to make it. And Felix, did you make it today? That's unfortunate. Okay. It is what it is. Anyone else? Last call? Okay. So then, if that's the case, I guess we can dismiss.